Okay, cool. So let's get started. So welcome to the security session. Thanks everybody for coming early in the morning. This should be a fun session. So we have 4 speakers lined up. I guess I'm the moderator, but I'm also going to give the first talk. I'll talk a little bit about Bitcoin and some other work we've been doing. Then we have Kevin Fu, who's going to talk about security and healthcare devices. So if anyone here is wearing a pacemaker, you'll be quite nervous after you hear Kevin's talk. Then we're going to hear from Giovanni, who's going to talk about malware analysis and web security in general, yes. And then Raluca will talk about privacy and enforcing policy in the cloud. So it should be a fun session. We're going to each talk for 15 minutes. So we should be done by 10:05 or so. And then we'll have time for 15 minutes Q&A. Then we'll have a break. And then we'll run into the next session, which is whatever it is. It's industry conversations. Yes, so that'll start at 10:30. All right. So with that, let me get started. So all 4 of us have actually done companies. I'm actually a happy camper. My company was acquired this year, so things are good. So instead of telling you about companies we've done, I wanted to tell you about kind of current research that we're doing. In particular, I'll tell you about 2 projects that we've done just very, very recently. So the first one is on Bitcoin. And you know, when you go pitch to VCs, the first thing they tell you is, like, on slide number 1, you're supposed to have some word somewhere. It's where you're supposed to have the words billions of dollars somewhere on slide number 1. Otherwise, the VCs don't pay attention to you. It's like the golden rule. Yes, so fine. So my billions of dollar slides is going to be on the Bitcoin capitalization. So you all know, you've all heard Bitcoin. This is kind of a graph. You can see Bitcoin kind of launched in 2009. This is the amount of dollars invested in Bitcoin. You can see it kind of took off seriously in 2013. It reached quite a peak, like mid-2013. Everybody thought, oh my God, this is going to take over the world. No more dollars. Everybody's going to be doing Bitcoins. Things kind of changed. It was a bit of a rough time in the last year and a half. So that's the beauty of technology. You can't ever quite anticipate how things are going to go. And today, you can see that in the last 6 months or so, things have kind of stabilized, and market capitalization is around $3.5 billion. Still very, very exciting. This is the first cryptocurrency that actually seems to work, that's actually being adopted. We've had lots of cryptocurrencies in the past, but none of them have worked. Yeah, they've all kind of worked experiments that never really took off. Bitcoin is among the first to really, really take off. And in fact, I really find Bitcoin exciting. There's really lots to do here. There's lots of crypto applications, lots of financial applications. So in fact, we just started a class on Bitcoin. You can see CS251. It just started on Monday on blockchain technologies. The thing that we're excited about Bitcoin is obviously the currency, but what's more interesting is even the applications of the blockchain, right? It's the first time when we have sort of an append-only database that's kind of, you can put things on it, it's publicly available, and no one can take elements off of the blockchain, and that by itself has enormous number of applications. So we're kind of excited about the blockchain and how to use it. So the course is focusing kind of obviously in the beginning of Bitcoin and also on blockchains. There are actually startups who are helping us build labs based on, in particular, a startup called 21, funded by Andreessen Horowitz, that actually helped us build a beautiful series of lab lectures and lab projects based on Bitcoin and Bitcoin mining. So if you want to teach a Bitcoin class yourself, please use this as a resource. There's a lot of work that went into building the homeworks and the projects for this course. So I would encourage you to teach Bitcoin courses yourself at your own universities, and please, you're very welcome to steal all the materials and use it in your own classes. Great. So unfortunately, Bitcoin is not all rosy. There are some issues also with Bitcoin. Of course, you may have heard there's a certain Bitcoin exchange that asks people to give them their Bitcoins, and it just forgot to give the Bitcoins back. Yes, so that was kind of an issue, right? That's kind of a bit of a disruption to this rosy world of Bitcoin. The question was basically, so after this happened, the question we were kind of curious about is, well, is there a way in which an exchange can prove that it's solvent? In other words, the number of assets, the amount of assets that the exchange has, could it prove that it has more assets than it has obligations? So this is the problem that we set out to solve. And in fact, we weren't the only ones looking at this. Greg Maxwell also looked at this problem. So we were kind of wondering, is there a way to ensure solvency? And essentially the problem is, again, if you look at what is the solvency problem, you have a Bitcoin exchange. It has a set of obligations, right? So there are customers who gave the exchange their Bitcoins. It's keeping the Bitcoins for them. So it has obligations to those customers, and then the exchange also has a number of assets, right? It holds its assets also in Bitcoins. And solvency is basically the problem of proving that your assets are greater than your obligations. Yeah, that's solvency. And by the way, you can generalize it beyond solvency to actually talking about reserve. If you just put an epsilon instead of in front of the obligations, you can, for example, prove that the assets are more than that half the assets are more than the obligations, right? So you can prove that you have a reserve instead of just a greater than or equal to. But I'll just focus on solvency, not so much reserve. It's actually the same problem. The issue is today, banks need to do this too, right? Banks also need to prove that they're solvent. And how do banks do this in the real world? Well, they hire an auditor. The auditor comes in, checks the books, and makes sure the bank is solvent. And then the auditor is kind of trusted to keep everything secret and to be honest. Yes, so there's a lot of trust in the system, and there's also a lot of expense in that the banks have to pay the auditors to do this job. The beauty of Bitcoin is that you need no trust in third parties, and this proof of solvency can be done without any expense, any payments done to a third party. Okay, so what our goal here is basically to prove that the assets are greater than the obligations, but do it in a way that doesn't reveal anything about the inner workings of the exchange. So this is what's called a zero knowledge proof, right? I'd like to prove to you that I'm solvent, and I'd like to do it in a zero knowledge manner. So you will learn nothing about my business, but you are convinced that I'm solvent. Okay, so that's what we set out to do, and this is joint work with two students, Dager and Buns, and with Joe Boneh, Jeremy Clark, and myself. And basically, it's an efficient zero-knowledge proof for this problem. And like I said, if Mt. Gox had run this protocol, their problems would have been detected much earlier than they were. So the idea is that a Bitcoin exchange would kind of run this every day, publish this proof, delete all the old proofs, but every day they would publish a proof of solvency. And if they ever can't do the proof, that means there's a problem, right? Then at least the public would know there's a problem. Maybe you should try to get your Bitcoins out. All right, so I'm not going to give you all the details of how this proof works. That probably is not appropriate for this audience. But I did want to give you a sense of how the mechanism actually works. Like, how do you prove that you're solvent without revealing anything else? So there are 3 steps to this process. And let me try and explain at a very, very high level how these steps work. So there are 3 subprotocols. So let's start with the first 2 steps, subprotocol 1 and 2. So the mechanism that we use is kind of a standard mechanism that comes up in zero-knowledge proofs. It's called a commitment. So a commitment, the way to think about this is I have a number x that I'm thinking about. I can take my number x, put it in an envelope, seal the envelope, and give it to you. Yes? Now, obviously, I'm committed to the number x because the x is in the envelope I just gave you, so I can't change the number x anymore, but you have no idea what the number is, right? It's in a sealed envelope. You cannot open the envelope, so you don't know what number I committed to. Okay, so a commitment allows me to commit to a value, so I'm committed to it, but you don't know what value I just committed to. Okay, so commitments are a useful concept in general. Here we're going to use them to prove solvency. Okay, so the first thing that the exchange is going to do is it's going to create a commitment to all of its obligations. Okay, so this means I'm going to sum up over all the balances of all my customers, and I'm going to commit to that sum. Okay, so now I've told you basically what my total obligations are. As we said, the commitment is binding, but it reveals nothing about how many customers I have, what's the total number of assets that I owe to these customers, and so on. Now, the beauty of these commitments is every user can actually be given some sort of a secret value. So the user logs into his account at the exchange gives him some sort of a secret key, and using this secret key, he can actually verify for himself that his balance was included in the commitment to all the obligations. Okay, now, how we do this, I'm not going to explain to you, but just believe me that we can make it so that every customer can be convinced that his balance is included in the total set of obligations. So if every customer checks that his balance is included, then we know that the set of obligations is in fact what it should be. But in fact, not every customer needs to check. It's enough that, say, 1% of the customers check. If the exchange cheats and actually does not include people's obligations, if a small number, a fraction of the customers actually check that the proof is valid, a corrupt exchange will be quickly caught, because a customer will see that his balance is not included, and then he can complain, and he actually has a proof that the exchange cheated him. OK, so that's step number 1, committing to the obligations. Step number 2 is committing to the total assets. So now this is kind of a difficult problem, right? So now the exchange has to prove how much money it actually has. But again, it's going to do it using these commitments. It's not going to tell you how many bitcoins it has. It's just going to give you a commitment to the number of bitcoins that it has. So how do you prove, this is kind of bizarre, right? How do you prove how many bitcoins I have without actually telling you which bitcoins are mine and how many there are total? So the way we do it is as follows, and this is something that's unique to Bitcoin. This is, I think, kind of the tricky part of this protocol. Something that you cannot do in the real world, but you can do with Bitcoin. So remember how Bitcoin works, right? In Bitcoin, there's this public blockchain. Every address in Bitcoin essentially is a public key for a signature system. So there are all these public keys out there. The exchange owns a subset of those public keys. Right? Those are the bitcoins that the exchange actually owns. And all the other public keys belong to other Bitcoin users. Okay? Now, what we'd like to do basically is here. So what the exchange does actually is it's going to choose, it's just going to go to the blockchain. It's going to choose like 1 million public keys. So n here could be a large number. It's going to choose like 1 million different public keys that have all sorts of balances associated with them. The exchange doesn't own all those 1 million public keys. Maybe it owns 1,000 of them. Maybe it only owns 10,000 of them. Yes, it only owns a subset of those public keys. What it does is now it can prove, again, in using this fancy zero-knowledge technology, that it knows the secret key for a subset of those 1 million public keys, and that the sum of the balances associated with those public keys is the assets that it just committed to. Okay, so I'll say it again. It's a little tricky. So we have 1 million public keys that were just pulled off the blockchain. So these are like random Bitcoin addresses. They belong to all sorts of random people in the universe. The exchange is going to prove that it owns 1,000 of those public keys, and the sum of the balances associated with those public keys is equal to the value, to the commitment to the assets that it just gave you. So this doesn't reveal how many assets it has. It doesn't reveal which public keys the exchange owns. It just proves that there is a subset for which it knows the secret keys, and the balances associated with that subset is actually the set of assets that the exchange committed to. That's the idea. So now how we do this, like I said, there's a lot of technical detail that I'm going to skip over, but just trust me that we can do this. So I hope this is clear. So now we've created a commitment to the obligations. We've created a commitment to the assets. The only thing we have to do now is prove that assets are bigger than commitments. Sorry, assets are bigger than obligations. And it turns out that's actually quite straightforward. This is like standard off-the-shelf technology. There's a way that if I can give you 2 envelopes, so 2 commitments. So I'll give you a commitment to X. So X is in an envelope, and Y is in an envelope. And then I can prove to you that X is bigger than Y without revealing anything about X and Y. This is just crypto magic that's old, and that's what we would use here to prove that, in fact, the exchange is solvent. So the cute part of this, so step number 3 is not interesting. Step number 2 is kind of the cute part that makes this problem interesting.
Can I ask a question?
Absolutely.
In that 1,000, what if outside of that set, the exchange, its biggest client, where they're holding most of the bitcoins, isn't in that 1,000? So they're only proving a sort of small subsection.
Actually, its customers are included in protocol 1, right? Those are in the obligations. So the exchange basically collects bitcoins from everybody. So it has like, let's say, Coinbase. They have like, 500,000 customers, say. It collects. Well, actually, I don't know how many customers Coinbase. I'm just making that up. So say it has 500,000 customers. It collects all the bitcoins from all its customers, and it stores those bitcoins in bitcoins that it owns, in addresses that it owns. what it's proving now is that the Bitcoin, that the addresses that it owns, well, it's committing to the sum of the balances with the addresses that it owns. So it's not, I mean, this protocol 2 is not related to what customers gave it. This is just basically how the Bitcoins are stored. Yeah? Cool. Excellent. All right. Very good. So fine. So that's at a very high level how this protocol works. Now we went ahead and actually built this, of course. And so let me just show you how this works. So here are 3 lines here. What the blue line shows you on the bottom, let's just look at, say you have 500,000 customers. So let's just look at the rightmost side of this graph. So you can see that verifying the proof is actually really fast. So on a single laptop, a customer can verify the entire proof in about 10 minutes. And in fact, a customer doesn't even have to verify the entire proof. Really, the customer is just going to verify that its balance was included in the commitment to the obligations and that the assets are valid. Yeah, so customers actually, if they wanted to verify everything, it would take 10 minutes, but in reality, they only have to verify a small slice. Sorry, that was actually, I'm sorry. The blue line is the time to generate the proof. So the exchange will take 10, just a second. So the exchange will take 10 minutes to generate the proof. Just 10 minutes. Yeah, question.
So if the proof fails, it just might mean that the sample that it shows wasn't large enough to prove that assets are large.
No, because remember, in the set of Bitcoin addresses that it used, it's going to have all of its addresses in that set. So necessarily, the set is large enough, necessarily. What is not being revealed is which subset of addresses it owns. Yeah, so imagine you could even, in principle, take all the addresses on the blockchain and prove, so that would be the anonymity set, yeah, and then prove that you own a subset of those and nothing else would be revealed about your set. Yeah?
So it's only zero knowledge in the limit of the size of the
It's sufficiently big. Well, it doesn't have to be. Now it's a policy matter, right? If you're comfortable in saying that a few of these million addresses are mine, then that's fine. If you want to reveal nothing, you would use the entire blockchain. And then you just say, some of these addresses are mine, but that's already known. Yeah, cool. That's a really good point. OK, so verifying the proof, let's see, that takes about 40 minutes. Verifying the entire proof, that's the orange line, takes about 40 minutes. But again, you wouldn't have to verify the entire proof. You would just verify a slice of it. And then the proof itself is, for 500,000 customers, it's about a gigabyte. So every day the exchange generates a gigabyte, stores it somewhere, throws away yesterday's proof. So storing a gigabyte in the cloud is nothing. That's pretty easy. Every customer just downloads its slice of the proof, verifies it, and we're done. Okay, so that's how this scheme works. So very practical. We've actually, we're trying now to get the Bitcoin exchanges to adopt this style mechanism, and we'll see how it goes. Okay, so I'm at the 15-minute mark, so I guess I'm going to skip over the control flow integrity, unfortunately. This was kind of a fun project I was hoping to tell you about, but I'll skip over that. I don't want to take too much time. So actually, I'll just tell you the punchline. Come on. Why doesn't this go forward? I'll just tell you the punchline. The punchline of this part is AES is a block cipher. Intel did amazing service to humanity, and they implemented AES inside the x86. This was inside their processor. This was an amazing success for Intel, to the point where now you see at every generation of microarchitecture, they're actually improving it. So Haswell is the old architecture. AES, one round of AES took 7 cycles. Skylake, which just came out this summer, now has been reduced to 4 cycles. In 2 years, it's going to get down to 2 cycles. So the message that I wanted you to take away from this is 2 messages. First of all, block ciphers, we used to think of them as being expensive to evaluate. They're basically free because of what Intel did. This is kind of remarkable. And second, it's going to be really hard, because of this, it's going to be really hard to promote any other block cipher, because any other block cipher is going to have to be implemented in software, and there's no way it will compete with what Intel did. So in some sense, AES is not going to be with us for many, many years to come. OK, so that's how, I guess I'll stop here. Last thing I'll say is OK, I need 10 seconds. So last thing I'll say is, at Stanford, actually, we have something called the Cyber Initiative. This is a big grant from the Hewlett Foundation that looks at the integration of technology into society. We're running a whole bunch of events in this space. So if you'd like to join or if you'd like to speak, please let us know. So you can see the type of questions we're looking at are ethics of data collections, privacy versus security. Is there really a trade-off? This question of data ownership. So if you'd like to speak or if you'd like to just participate, please come or please let me know, as I said, if you'd like to speak. OK, with that, I will stop here. And I guess we'll move on to the next speaker. Why doesn't this advance? Here we go. We'll move on to the next speaker. So thank you very much. And